5 of irrational functions. It's the last section in chapter 4. And we're kind of pulling everything together that we know so far. So we've already kind of graphed some things by hand earlier in chapter 4 with the polynomials by finding their zeros and graphing those on the x-intercepts. Talk about the end behavior, are they both going up, are they both going down, that kind of thing. We're going to pull all those concepts together, but what's different in this section is that they're not polynomials, they're called rationals. The root word in rational means ratio. So what you'll notice is our polynomials are the top and bottom of the ratio. So it's basically just really ugly fractions is what we're going to be graphing. And it's pretty cool to see that we can graph it by hand without using our calculator, all right? So it says a rational function is a function f that is a quotient, aka division, right, of two polynomials, p of x over q of x, where p and x and q of x are both polynomials. Q of x cannot be 0 because we can't divide by 0. And then we'll talk about domain. We talked about domain a long time ago, like the first test, right? The domain of f will consist of all the values of x that don't make the denominator x. Everything else will be okay. So the first couple of questions in your homework and on your worksheet will be, let's just find the domain. All right? So the domain, and then we're going to use transformation. So that was like shift left, shift right, that kind of thing. So let's talk about the domain first. In polynomials, your domain can be any real value. So you can cube things, you can square things, big or small, it doesn't matter. But here, when we have a denominator, what do we want our denominator never to equal? 0. So remember how we would steal the denominator, set it equal to 0, and say, don't be that number? That's what we're doing.
So x can't be negative.
You got it. But remember, when you say domain, you're not supposed to be stating what it can't be. You're supposed to be stating what it can be. So we have to write this in interval notation where we want to say every number but negative 4. Remember how to do that? Negative infinity to negative 4 union negative 4 to infinity. Okay? What does that mean? That means that we can graph every x on here, so we'll have a continuous line, except for we cannot graph x equals negative 4. All right? So that's the first part, our domain. The second part says use transformations. Okay? This one's a little bit different because we didn't really graph the parent function very much, but our parent function, guys, was called the reciprocal function 1 over x. And I forget what, it's in chapter 2. Maybe it's in, I think it's 2.5. So we learned about all the parent functions. Remember, like x squared was a parabola, x cubed was that snake, all kinds of stuff. The 1 over x was one of ours. And just to kind of give you, like, let's just do a rough sketch of it real quick, okay? So what we had was we had the x and y axis. And we kind of had like this weird little u that fit into the third quadrant. And this weird little u kind of thing that fit into the first quadrant. Do you remember graphing that as the reciprocal? So as x gets really, really big, 1 over x gets really, really small. So when we go out to infinity and negative infinity, our y values are really close to 0. But if you do like 1 over 1/2, that's the reciprocal. So 1/2 goes to 2 and so forth. So the smaller x gets, the more extreme, right? So you guys did awesome on the test, the transformations. The parent function is just normally 1 over x. But notice we have a plus 4 inside the function. So was inside a horizontal or a vertical movement?
Horizontal.
Yep. And is it to the left or is it to the right? Left, exactly. So remember, anything on the inside was horizontal and was the opposite of what you want. So we want to graph this shift to the left. So all we have to do, guys, is realize instead of having this vertical line that we don't cross here at the y-axis, we're going to shift it 4 units to the left. 1, 2, 3, 4. And we'll talk about what this means. We're going to do a dotted line real quick. And we have not actually defined it. It's actually the definition right below here. It's called a vertical asymptote. Okay? A vertical asymptote is an x value of the graph that you never cross. All right? So how are we going to fit this in? Remember, he's kind of like that U shape that just fits into that little corner. But now the corner's just shifted over 4 units. And it's just one that we're not very comfortable with. But this is what our rational functions are going to look like. So we got to get comfortable to these weird looking ones. So on your MyMathLab, on your worksheet, the first couple questions are just asking you to find domain. Notice when we draw these arrows, do we go to negative infinity? Yes.
Yeah.
Do we go to positive infinity?
Yeah.
Yes. What's the one x value that we never hit?
4.
Negative 4. There's a visual of x being not negative 4. Okay? Notice we cover every x value except for this one right here. Okay? So now what we're going to do is we're going to learn about asymptotes. Okay? So vertical asymptotes, let's go ahead and read the definition. It says for a rational function f of x, where p of x is over q of x, just kind of like we defined up there. If a is a 0 of the denominator, so kind of like what we did up here, negative 4 would have been a 0 of the denominator, then there's a vertical asymptote at x equals a. All right? So remember, vertical lines are defined x equals a constant. So the vertical asymptote is just wherever you have zeros of the denominator. The key thing, though, that I'm going to point out now, and it's going to be fine, like I don't have to point it out at all, but I'll try to throughout the notes. We don't talk about it till the very end. But you're not a vertical asymptote until you realize that p and q have no common factors, meaning you need to factor the top and you need to factor the bottom first and cancel out any common factors if you can. Then whatever remains is your vertical asymptote. All right, so let's go ahead and look at the bottom here on example 2. They want us to find the vertical asymptotes, all right? So the vertical asymptotes come from the zeros of the denominator. So our vertical asymptote, we're going to take x squared minus 4 and set it equal to 0. How do we solve for x? Yes, okay, so there's many ways we can do this. One way, which I don't think you guys are as comfortable with it as I am, is realizing that's a difference of 2 squares. So it factors to x plus 2, x minus 2, right? Another way is what Corey mentioned, that she noticed we have a square and a constant, so we can just move the constant to the other side and take the square root, right? So this is x squared equals 4. How do you undo squaring? Square rooting, but when you square root, what do you put in front of that square root? Plus or minus. So x equals what? 2 and negative 2. Okay, so those are your 2 vertical asymptotes. What does that mean? It means, well, they haven't asked us to graph this guy yet, but if we did, it kind of looked like above, where we'd have a dotted line down negative 2, and we'd have a dotted line down positive 2, and we would not cross those vertical asymptotes, all right? So it's kind of weird, but vertical asymptotes are basically exactly the opposite of a domain, right? Domain is every x you can have, and the vertical asymptotes are the x's that you can't have, all right?
So, like, say if it was 2 and negative 2, you just wouldn't touch any of them?
Right, so you'd do like a dashed line down negative 2, and whenever you were graphing stuff, you'd make sure to never cross that line. Okay.
So it can even be like 1 or 0?
Yeah, it can be anything. We're going to play with all kinds of vertical asymptotes. All right. So we also can have horizontal asymptotes. So that is a horizontal line that we might not approach, and how we come about it is totally new to us. So this is going to be the new part of section 4.5. So let's read this. Again, it looks more confusing than what it really is. It just says a line y equals b. Well, keep in mind a horizontal line is y equals a constant. So that's all it means. Vertical asymptotes, x equals a constant. Horizontal asymptotes, y equals a constant. All right? So the line y equals b is a horizontal asymptote for the graph of f if either or both of the following are true. This is like calculus notation right here, okay? As f of x approaches b, meaning the y part of your function gets closer and closer to that line of whatever, as x approaches infinity, or as y gets closer and closer to that constant, x is approaching negative infinity. Basically, it means you have this line and like you're kind of like here. Let me show you. You see how we approach positive infinity? What is this getting closer and closer to? The x-axis. So that's y equals 0. And see how we approach negative infinity? What's that getting closer and closer to? The y-axis. So this y-axis, or excuse me, x-axis here, is a horizontal asymptote. So it's just like a vertical one, but sideways. How to find them is a little trickier because there's 3 methods. All right, so let's see if I can make it make sense to you. When the degree of your numerator, so let's underline that. The degree of the numerator, everybody know what a numerator is? The top number, right? Is less than the degree of the denominator, then there's no thinking. There's literally just memorizing. If the degree of the top is less than the degree of the bottom, so let's write bottom there, then the y equals 0 is your horizontal asymptote. And this, I can prove it, but I'm not going to prove it in the fancy, correct way. I'll just kind of talk to you about it. Remember the whole idea of vertical asymptotes is as x is getting bigger and bigger and bigger. So I know it's kind of weird because I'm going to put air quotes in here. X is approaching infinity. So what's the top approaching? Infinity. It's getting big, right? But down here, x is squared. So it's approaching infinity even bigger and quicker. So what happens when you take a small number and divide by a bigger number? It gets closer and closer to 0, okay? So if the degree on top is smaller than the degree on bottom, then basically the bottom rules. He's the stronger guy. He's like, I'm going to get bigger way quicker than you are, so I'm going to go to infinity. But 1 over infinity is basically 0. Or 1,000 over infinity is basically 0. And so that's kind of the thought process behind it. I can prove it with math, but I'm not as worried about it. So what we're just going to note is we're going to always look at the degrees, because that's going to help us decide what our horizontal asymptote is. So what's the degree of the top? This is the first degree. Do you guys agree? Or degree 1, that's fine. And what's the degree of the bottom?
2.
Yep. So according to this, if the top is less than the bottom, our horizontal asymptote is just what? Y equals 0. Meaning the x-axis.
It can't be that easy. What if it doesn't equal 0? That's when it gets hard.
Yeah, and it's not even hard. It's not hard, it's just a different, I'll show you. It's actually part 2 that we're going to do here in a second, okay? So that one just, these steps are more like memorizing than making it click kind of thing. Just remember, if your degree on top is smaller than the degree on bottom, the bottom's growing really, really quick, and the degree on top's not growing as much, so it's getting closer to 0. But she's already getting suspicious, like, I know it can't always be 0, so when is it not 0? Let's look at number 2. When the numerator and the denominator of a rational function have the same degree, then the line y equals a over b is the horizontal asymptote. You're like, where the heck is where's a and b coming from? A and b are just the leading coefficients of the top and bottom, okay? So let's look at this. So I kind of want to like underline stuff. So when the numerator and denominator have the same degree, then the horizontal asymptote is just y equals a over b. All right. Again, I'm not really going to prove it mathematically, but I'll kind of talk to you kind of figuratively. Do you guys, looking at this next example, agree that they're both the third degree polynomial, right? Degree 3?
You just go by the biggest degree.
Well, we're going to look at both, and we're going to talk about it, because every scenario is different.
Because it has another one too.
Oh, yes. Remember from 5.1, the degree of the polynomial is always the highest degree. Yep, perfect. That's what you're asking, sorry. All right, so the whole idea here is if x is approaching infinity, it's approaching infinity cubed up top, and it's approaching infinity cubed on the bottom. So the whole idea is that it's growing just as big pretty quickly. So all this stuff's kind of canceling out except for this leading term. So this is the a over b that they're talking about, guys. A is just the coefficient of the first polynomial. B is just the coefficient of the bottom polynomial. So if they have the same degree, which these do, your horizontal asymptote is just the line 3/5. You see where 3/5 came from?
Yeah.
Okay.
Why is that so easy?
No,
It-
that's super easy.
It is.
It's a trick.
It's not a trick, I promise. It's not.
It's a try.
No. So if the bottom's growing quicker, we're going to approach 0. If the top and bottom are kind of growing at the same rate, we're just going to look at the leading coefficients, 3/5. All right, so then the one thing we haven't done is if the top is bigger than the bottom, that's where it gets a little tricky. Yeah, that's the catch. And we're going to put them to the side for a second, but it says when the degree of the numerator, so the degree of the numerator is greater than the degree of the denominator, we do not have a horizontal asymptote. We actually have an oblique asymptote, okay? Your obliques are your, the sides of your abs or whatever, but in math, an oblique just means a diagonal line. So it's like any other line you're used to graphing, right? Most lines we graph are diagonal. They're not straight up or straight over. And we'll talk about it in a second, how we can figure out that line and how to graph it, all right? That's usually not the most common case, but we are definitely we're gonna cover all of that, okay? So how do we figure out horizontal asymptotes? We're gonna look at degrees. If the degree on top is smaller, then it's getting shrunk to 0, so our horizontal asymptote is y equals 0. If the degrees are the same, they're growing about the same rate, so that leading coefficient, 3/5, is going to be our horizontal asymptote. And if the degree on top is bigger than the degree on the bottom, then there's no horizontal asymptote. We actually have an oblique asymptote, which is a diagonal line. We'll make note of that. And we will specifically talk about that here in a second, okay? So what do we need to know about asymptotes? There's two types. Well, I guess there's technically three. There's the vertical. So in rational functions, there's always a vertical asymptote. And the key thing to note is we never cross it. You never cross a vertical asymptote. You never cross a vertical asymptote, okay? Now, with horizontal asymptotes, a majority of the time you don't, but sometimes you do, okay? So there's this might idea there. You may cross a horizontal, okay? So you might cross a horizontal. So I'm just going to draw you some pictures real quick. And it's kind of hard because, like, pick a random line. It doesn't matter. So, like, I'm going to count over to -3, 1, 2, 3, and I'm going to do dashed line up and down. There's my vertical asymptote. And I'm randomly picking this. I don't have a function that goes with it or anything. We just want to draw a couple examples of when you do and when you don't. I'm going to just count up to 1, 2, and do a horizontal asymptote real quickly. So here, I'm going to fit him right in here, kind of like we did before. And I'm going to fit him right in here like we did before. This is a case where we're crossing neither, okay? We're going to get as close and close to the vertical asymptote as possible, coming in from the left and the right. And we're going to get as close and close to the horizontal asymptote as possible, coming in from the bottom and the top. And we're never going to cross either one. All right, there it is. Here's another example. How did I do this? I think I randomly picked. So pick 1, 2, 3 again, go up and down. Now let's do +3, 1, 2, 3, go up and down. And I'm going to pick -4, 1, 2, 3, 4, and I'm going to go across. And you're like, Molly, where are these coming from? Well, remember, our vertical asymptotes come from our denominators. So this means this would have had a denominator of x plus 3. This means it would have had a denominator with a factor of x plus 3 and x minus 3. So that means it was x squared minus 9 on the denominator. And then remember, the horizontal asymptotes come from the leading coefficients, okay? So how could this guy look like? Maybe he's like this, in this little corner. But then we have this like cubic function going in, and he's crossing that asymptote, right? And then we have this guy. Isn't this crazy? We're going to be graphing these things. I know. It's not. It's step by step. Remember my skeleton? We're gonna do step-by-step skeleton. This is just an example of where we have two vertical asymptotes, and notice on both of these vertical asymptotes, we're never crossing them, and you never will. And then technically this is a horizontal asymptote because as we go out to infinity, this direction we're approaching it. And as we go out to negative infinity, this direction we approach it. But look what happened right in the middle.
You could
we did cross it, okay? So it may or may not happen. And then last but not least, we'll do this one more time. No, I think that's good. That's enough examples of when you don't and when you do, okay? Thank you. So let's see if we can get this next problem done, and then I'll stop the recording so I don't get cut off. So this is going to get us to start sketching without using our graphing calculator, okay? So part A is first identify the equation of any vertical asymptotes. Remember, your vertical asymptotes come from the bottom.
So it can't be, it can't be 0.
Right, what can't be 0?
-3.
Right, so we're going to set x plus 3 equal to 0, which means x equals -3 is the asymptote, right? So like, you're used to saying x can't be that because they asked for a domain, right? X cannot be -3 because if it was -3, the denominator would be 0. But when they ask for a vertical asymptote, they want to know where that vertical asymptote is occurring. It's occurring at that hole. So it is equal to -3. How confusing is that? So remember, vertical asymptotes and domains are opposites of each other. Domain would have been everything but -3. The vertical asymptote is -3. So let's go ahead and graph that real quick. So we'll count over 3. 1, 2, 3, and we'll do a dashed line. Try to make it as dark as possible. It's hard to do it, okay? And I'll just put vertical asymptote of x equals -3. All right. Let's find the horizontal asymptote. And this is the one where it's basically just pure memorization, guys. We're going to look at the degrees of our polynomials. This is of degree what? 1. This is of degree 1. When they match, it's the leading coefficients, right? So what is the leading coefficient? 2 over 1, exactly right. So y equals 2 over 1 or 2. So y equals 2 is our horizontal asymptote. And we can graph that, right? We're going to go up to a y value of 2 and do a horizontal line across. So you can kind of start anywhere. I always start at the origin for some reason. 1, 2. So we're going to just go this way. Is that okay? And I'll write just HA for horizontal asymptote, y equals 2. All right. So now we have our graph kind of split into like 4 little quadrants, right? And what we want to do is we want to pick like 2 points that are to the left of the asymptote, so we'll know, are we going to graph up here or are we going to graph down here, because it's never both spots. And then we want to pick 2 spots to the right of our vertical asymptote, so again, so we know, are we graphing up here or are we graphing down here, okay? So let's find, and I usually kind of stay close to it. So our vertical asymptote was at -3, so let's find out what f of -4 is and f of -5. Guys, how do you find a y value when you have an x value and you have a function? What do we need to do with that x? Plug it in, right? So f of -4 is just 2 times -4 all over -4 plus 3. Do you guys agree with that? Just plugging it into our function. 2 times our x of -4 all over -4 plus 3. So this is something where you're going to want to do kind of like step by step, like figure out your numerator first, figure out your denominator, and then divide. Because if you don't have parentheses in the right exact spots, your calculator is going to calculate it wrong, okay? So what's 2 times -4? -8. Yeah, and it's not over 1, it's over -1, right? So what's a negative divided by a negative? You got it. So what's an ordered pair we can graph? -4, 8. Is that okay? So let's go plot him. We're going to go over 4. 1, 2, 3, 4, and up 8. 1, 2, 3, 4, 5, 6, 7, 8. There he is. All right, let's find f of -5. We're going to do the same thing. 2 times -5 over -5 plus 3. Well, what's 2 times 5? 10, so we'll have -10 down there. Is that okay? And then what's -5 plus 3? -2. What's the negative divided by a negative? Positive. So what's 10 divided by 2? 5. So what's our ordered pair? -5, 5. All right, so I'm going to go back up here and graph it. So this was at 3, so this is 4, 5, and I'm going to go up 5. 1, 2, 3, 4, 5. Can you keep going? Sure, but we know exactly what it's going to do. Remember, the whole idea of an asymptote is that you're going to get closer and closer to it. So what is this going to look like, guys? Something like that, right? So notice we didn't have to pick a bunch of points. We had to just know which area was it going to be in. Was it going to be in this square or this square? Because otherwise we know it's just going to be shoved and getting closer and closer to both asymptotes. All right, guys, I know there's not a whole lot of room, but we need to do this exact same thing again, but with a couple points on the right side of the asymptote. So do we know if we're going to graph up here or we're going to graph down here? Okay? Yes, ma'am. What?
I tried to do 1, 2, 3, 4.
And it's hard because I feel like on the graph, the original X and Y didn't graph very dark. You got it? All right, so I'm going to go ahead. Since our vertical asymptote was at -3, I'm just going to pick f of -2 and f of -1. Okay? I'm just going to do the same thing. 2 times my x value of -2 over -2 plus 3. Well, 2 times -2 is -4. But -2 plus 3 is a positive 1 now. So what's our y going to be? -4. So we can graph the point -2, -4. And I'm going to go do it right now, okay? So this is my origin. I'm going to go to -2, 1, 2, and then down 4. 1, 2, 3, 4. And then you kind of have an idea what's already going to happen if we're plotting that point down there. We know the whole graph's going to kind of be shoved in here. But it's nice to have a second point to know exactly what we're doing, okay? So I know it's kind of tight on room. I wrote a little bit big. We're going to do 2 times -1 over -1 plus 3. Well, like 2 times -1 is -2 over -1 plus 3, but that's just 2. -2 divided by 2 is a -1. So our final point we're going to plot is -1, -1. So I'm just going to go find it. Okay, let's see. This is my origin. Go over 1, down 1. But again, we kind of have an idea of what our graph's going to look like. He's just going to go like this and kind of get as close and close to the asymptotes as possible. It's just kind of cool to think that you guys just graphed this crazy rational by hand without putting it into your graphing calculator. Did you ever think you could do it? No. And we're going to get even more exact. Like this is kind of a rough estimate because notice here, excuse me, notice here we crossed the x-axis and we didn't really see where. That's going to be part of our steps here in a second, okay? So when we get further into this note packet, we're going to be finding our intercepts, x and y and all that kind of stuff. So we'll have more points to graph to be more accurate.